Right, so we're doing FRQ 1995 B3. This FRQ gives us a cart and a track that goes flat, goes uphill, goes downhill, goes through a loop, and it ends. And the cart here has a string inside. It suspends a zero point 0.1 kilogram ball, and this will change position, and the tension will also change as the cart moves throughout the track. So knowing that, first question says to draw and label all forces acting on the ball when the car is at rest at point A. So at this point, there's only two forces, and that is tension acting upwards and there's gravity acting down. And both forces are equal since, you know, first of all, the ball is at rest. That means there's no net force. So the gravity pulls down and the tension pulls up at the exact same magnitude. So these are counteracting each other. Knowing that, we go into part two, which says to calculate the tension. Tension, use the 0.1 times 9.81. That's mass times gravity. And that gives us the weight, which is 0.981 newtons upwards. And since tension and weight are the exact same magnitude, that's how we calculate it. It's just in a different direction. Now we move on to the next portion. This portion gives us four situations at each location in the track. And it says to calculate first the horizontal tension, the vertical tension, and then to approximate the location of the ball in relation to the cart. So what we're doing is for part B, the car is moving to the right with an acceleration of 5 meters per second squared. So all we have to find is the net force on this ball. And to do that, we plug in the mass, plug in the acceleration, 0.1 times 0.5, that's zero point 0.5 newtons. And that's a net force acting in the horizontal direction. And that gives us the horizontal tension, because if that's the only horizontal force, then it must be provided by this tension. So essentially, the string is pulling the ball with 0.5 newtons to the right. For tension vertical, it's the same as the original, which is 0.981. The car is not accelerating up or down, so vertical tension remains the same. Move on to part C. Part C says the car is at point C moving up at 30 meters per second. It's moving uphill. So for this part, there's no acceleration, net force is zero. Since net force is zero, there's actually no change in the tension. So horizontal tension is zero, vertical tension is 0.981 newtons, and the ball is just straight downwards. It's not moving left or right. There's nothing that is pulling it besides gravity. If we look at part D says the car is moving downhill with a acceleration of 5 meters per second squared. So in this case, we have to use trig. We have to find each component. So if you just look at it unresolved, 0.5 newtons is the net force. That's using the same method in part B if it goes MA. That's the net force that is acting on the ball. So this time it's acting at an angle downwards. To find the horizontal and vertical forces, we need to use trig. 0.5 cosine 30, that gives us the horizontal force, and then 0.5 sine 30, that gives us the vertical force. Knowing those, we can now solve for tension. So if we look at this algebraic equation, F equals ma, we can replace ma with tension plus mg. Since the net force is, there's only two forces, so the net force is the difference between tension and gravity. or weight. And then when we isolate for tension, we get tension equals force minus weight. Force in this case, if we're solving for vertical tension, is ma sine x. That is the net force times sine x to give us the vertical force that is acting on the ball. And we subtract weight to get tension vertical. But because of the direction, net force is actually negative because it's going down. And gravity is also negative, but there's a double negative here, so that just becomes positive. So essentially it's gravity minus the force in the vertical direction. And when we solve for that, we get 0.731 newtons as our vertical tension. If we look at tension horizontal, it's just 0.432 newtons, and that is just the horizontal force. Since that's the only force acting horizontally, that's the only the tension has to provide all of that. But in the case of vertical tension, gravity is also acting down, so that's why we have to factor in both gravity and the net force acting downwards. We look at part E. Oh, by the way, the ball will be like this. It'll be sort of aligned with the cart because it's actually being pushed back as the car moves downhill. Same as in part B. Since the car is accelerating forward, the ball is being pushed backwards. It's like when you're in a car and the car accelerates and you get pushed back into your seat. That's the same principle that's going on here in both B and D. Then we move on to E. In E, the car is upside down at the top of a loop. It is moving at a constant 25 meters per second at that point, and the loop's radius is 25 meters. So we have this equation, force centripetal equals mv squared over r. So we can solve for that. And we know that force centripetal is made up of two forces, that is weight and tension vertical, because both of those forces are pulling towards the center of the loop. So we set it up like that, we substitute, and then we can isolate for tension vertical. We know the weight and we know the centripetal force. So we can just add those, or subtract those, I guess. And that gives us tension vertical, which is 1.519 newtons. And that's basically just the difference between the weight acting down and the overall centripetal force acting down. For tension horizontal, it is 0, since the car is actually not accelerating at this point in the horizontal direction. So the ball is just going to be straight like this. It's going to be straight up and down, just like it would be, but upside down. And that's it.